Hey guys, welcome to another video about data encryption standard, which is a very important security protocol. So in this lecture, we are going to talk about this protocol, its background, how this works, the different components of the DES algorithm, and finally, we will see some security drawbacks of the DES algorithm. So let's start with the historical background of the DES algorithm. DES actually stands for Data Encryption Standard, although it is not considered to be a secure algorithm, but still it is important to study for several reasons. Why? Because it was a standard security protocol for decades. This was the most widely used encryption scheme before other encryption algorithms like Advanced Encryption Standard or S. Also, the reason for considering this for study is that it made use of techniques that were not previously used, and therefore it set a bar high for all the cipher that follow the DES algorithm. Another reason for studying DES algorithm is that it was developed from a secret collaboration between the NSA, National Security Agency, and IBM for a publicly available cipher. There had been some prior interactions between the NSA and different industry partners, but nothing was go public. So you can say DES was the first effort to make it available for the general public, and it was collaboration between NSA and IBM. The efforts for DES came back to 1973. It was the National Bureau of Standard NBS, which is now known as NIST, National Institute of Standards and Technology. Actually, in 1973, NIST and NBS they make a call for proposal for a standard data encryption algorithm so that it can be used by federal agencies for cryptographic protection of sensitive information. Then, as a result, the NBS, along with the NSA, choose an algorithm that was developed by IBM, and that algorithm was known as Lucifer. And finally, the Lucifer was adopted in 1977 as standard DES algorithm. The man behind DES algorithm is known as Facile. I think the T here is silence. Facile. Okay. Actually, he was an IBM employee. As I just mentioned, it was an effort made by the IBM, and the man behind it who was actually working at IBM is the Horst Facile. And he has been credited as the creator of DES, although there were other people involved as well. He himself want to call the system as data seal, but IBM used the term demonstration cipher, and the later on the demonstration cipher was referred to as a demon cipher. But finally the name was changed to Lucifer, and here the cipher is for cipher. Okay. There were other names that were used for the same algorithm like DSD1, but the most commonly one is Lucifer. And Lucifer was used by one of the Bank of London for cash system in 1970s. Then after the Lucifer, the National Bureau of Standard, as I mentioned, they held a competition for a cipher system so that it can meet the civilian needs. And this system was called as data standard encryption. And surprisingly, Lucifer was the only algorithm that was accepted by the NBS and by the NSA advisors. So Lucifer was adopted as a standard in 1977, and its final name was changed to DES at that time. So this is a historical background about the DES algorithm. Now let us see overview of the DES algorithm, some properties, characteristics. Actually, it is a block cipher. You remember we have two types of cipher, the block cipher and the stream cipher. Block cipher mean it will have to operate on standard block size of the data, mean the data or the input is divided into different blocks and each block is going to be of same length. So it is actually a block cipher. On the other side, it is asymmetric cipher. It is a symmetric cipher, and symmetric cipher mean we have to use the same key both for encryption as well as for decryption. As it works on block of data, so actually it take 64-bit plain text and then it will create a 64-bit cipher text. So you can say that this algorithm will actually take an input of 64-bit and it will convert that input into 64-bit output or the plain text to ciphertext. And on the receiver side, the decryption process happen in a reverse order. It will take 64-bit ciphertext and then it will derive 64-bit plain text from that cipher. Another property of the DIS is that it is an iterative algorithm. Iterative mean, as we will see in a moment, it has different rounds. So the block of data has to be passed from different rounds iteratively. And the total number of rounds that are in the DIS is 16. Why so much rounds? Because it is considered that the more rounds an algorithm has, the more secure the algorithm would be. However, if you see on the right hand side here, the DIS algorithm uses a key of only 56 bits. And this is one of the major drawbacks, as we will see at the end of this lecture. So it uses a key size of 56 bits. Actually, in reality, 64 bits are used for the key. However, the remaining 8 bits, they are used for parity checking, and they actually have no effect on the security of the DES algorithm. And every 8 bit of each byte, that is actually used for parity checking. Okay, after discussing the overview, let us see two important properties that we will be discussing later on. The first one is confusion, the second one is diffusion. Confusion is actually the relationship between the key and the ciphertext, and we want to make this relationship difficult to understand. A common method, this is a common method which is used for making the algorithm secure. The DES algorithm actually uses a technique which is known as substitution to achieve the property of confusion. The next property is known as diffusion, and in a broader sense, it is actually the relationship between the plain text and the ciphertext. And it means that the influence of one plain text symbol is spread over many ciphertext symbols. And why? Because we have a goal in mind, and that goal is to hide the statistical properties of the plain text. Confusion is normally achieved by substitution, while diffusion is normally achieved with permutation. And we will see that this will achieve both confusion and diffusion with the help of substitution and permutation. So if later on in this lecture, if you see substitution word, it means confusion. If you see the permutation word, it means the diffusion property. And any algorithm that actually make use of a confusion and diffusion properties, we can say that it is more secure algorithm. What is permutation? To understand the concept of permutation, we have a figure here. Permutation is actually the act of arranging all the members of a set in some sequence or in some order. For example, you have a set of three numbers 1, 2, and 3. Suppose the color of 1 is red, the color of 2 is green, and the color of 3 is blue. So the different ways by using which you can actually arrange these elements of the set is known as permutation. So you can see here we have 6 different ways by using which we can arrange these elements of the set in some sequence or in some order. Now let us see how actually this work. The overall process of DES encryption is shown in this figure. As you can see, it seems like a bit complicated figure because there are many factors involved here. Like you can see, we have the input at the top, we have the output at the bottom, but in between we have things like initial permutation, inverse initial permutation, and we have left side of the input, right side of the input, and then we have a function, we have a combination of keys, we have exclusive OR operation and things like that. So there are different steps. Okay, so after looking at the figure, we actually conclude that the plain text, the input, actually proceeds in 3 different phases. In phase number 1, the 64-bit, remember the input to the DIS is actually 64-bit. So the 64-bit input, actually first it passes to initial permutation, and you know what permutation means. This permutation will actually rearrange the bits to produce the permuted input, as you can see here. That is the first step. The second one is actually followed by a phase which consists of 16 rounds. And in every round, we are actually using the same function. And this function, as we will see in a moment, it actually involves different things. We will see that it will involve permutation as well as substitution functions. And if you give attention to the final round number 16, after that, the output of the last round, it will actually consist of an output which will actually contain 64-bit as well. And that is make as an input to another function, and that is the inverse permutation. This is actually round number 3. So in first round, we perform initial permutation on the input. In second round, the permuted input, goes through 16 rounds. And then finally, the output of the 16th round is actually given as an input to another permutation, which is known as inverse initial permutation. And it is actually the inverse of the initial permutation that we have used here. And it will finally produce a 64-bit cipher text. One important thing that is very much technical is mentioned here. After round number 16, we actually sweep the two output. Why? The sweeping is important because the decryption algorithm in this way, the decryption algorithm will have the same structure as the encryption algorithm. Okay, later on we will see. We are focusing only on the encryption process, but the decryption process is opposite. So this sweeping is important to make the encryption and decryption algorithm compatible with one another so that they can perform on the same round with the same key. Okay, so that is why we have a swapping after round number 16. Okay, we talk about a function that is used in every round. This function is important and it is made from several components, and we will see it in a moment. Another thing to remember here or to understand here is the key, the concept of the key, 56-bit key. And you will see here that this is the same way, the same figure, but we are trying to look at it from a different angle. You see, we have the 32-bit left hand side, we have the 32 bits right hand side, and this is actually the function, but here the function is like explode, and you can see 4 different components here. And then the output, the right output is gone to the left, and the left hand side is gone to the right after exclusive OR. What we are going to focus here is on this right hand side, which is actually the key. 28-bit will give you 56 bit, so the key is 56-bit. And then we perform different operations like left shift and permutation and things like that. So here we get a key, and that key is going to be different for each round. So ki, which mean ki mean k1, then it will be k2, k3, k4 up to k16. So initially the key will be passed from permutation, as you can see here, permutation function, and then for each of the 16 round a subkey ki is produced by the combination of the left circular shift and a permutation. The permutation function is the same for each round, but a different subkey is produced because of the repeated shifts. And this is important for security purposes, that we will get a different key for each and every round, although the permutation function is the same. But due to this shift operation, we will get a unique key for each round. Well, if you see at the disk, it seems a bit complicated. So it's important to understand the disk and how it's work by looking at the individual pieces that it is made out of. And the most important components that we are going to explore individually are initial permutation, final permutation, the function f, and the components like the expansion table, substitution boxes, and exclusive OR operations. So we are going to open these components and study them one by one. So first let us see what is initial and final permutation. This is initial permutation, this is the final or inverse permutation. So we are going to talk about these two elements now. The initial permutation and the final permutation, they are actually bitwise permutations. Bitwise mean they operate on individual bits. And it is like a cross wiring, just to mix the bits. Okay, it is important to note that these two permutations have no cryptographic significance in disk. They do not increase the security of the disk at all. Both permutations are keyless and predetermined. Keyless mean we are not using any key. Predetermined mean their design is known. Okay, now the question is why? If they have no effect on the security, then why they are there? Why they exist? So the exact rationale, the exact logic for the existence of these two permutations is not known. Nobody seems to know why the designer bothered to rearrange the bits of the plain text, although it has no cryptographic effect. But that is how the disk has been defined. We do not know the exact reason. However, it is believed that their original purpose was to arrange the plain text and ciphertext bits in a byte-wise manner to make the fetches easier for 8-bit databases. In 1970s, the state-of-the-art registered size was that one. So to make it compatible with those registered, it is assumed that maybe the design is considered to be like this. Okay, so you can see here we have, these are actually called as P boxes, the permutation boxes, and it is shown in the figure. Each of these permutation actually takes a 64-bit input and then it permutes them according to a predefined rule. Okay, and these permutation are, as I mentioned, they are keyless permutation, and they are actually inverse of one another as well. For example, how they work, let us see. In the initial permutation here, you can see that the 58-bit in the input, it will become the first bit in the output. Similarly, in the final or inverse permutation, the first bit will become the 58-bit in the output. So you see they are actually inverse of one another. In other words, if the rounds between these two permutation do not exist, then the 58-bit entering the initial permutation is the same as the 58-bit leaving the final permutation. So they're actually inverse. And the permutation rules which input bit is going to be replaced by which output bit, it is actually predefined in these P boxes, and they are shown in these tables. Each side of the table can be thought of as a 64-element array. You have 64 elements, and the values of each element actually define the input port number, and the order, the index of the element defined by the output port number. For example, you can see initial permutation table here. So it means that the 58-bit of the input will actually take the location 1. 50-bit of the input will actually take the location 2, and so on. So this is about the initial and final permutation. Next component to explore is the number of rounds. So as I just mentioned, we have a total of 16 rounds. Okay. What is round? The basic unit, which we know known as a block. So the block on which the algorithm works, they are actually 64 bits, or you can say 8 character long. One operation used in the DES actually consists of breaking the 64-bit message block into two halves and then switching the side as depicted here. Let me go back here. You see we have 64 bits here, and then we divide it into two halves. 32 bits left side, which is represented by L0, and 32 bits right side, which is depicted by R0. R stands for right. So in each round, at the beginning of first round, we actually divide the input into two halves, 32 bits and 32 bits. And then we switch them, like in the next round, the left side will become the right, and the right side will become the left side. As you can see here, the right side will become the left, and the left side will become the right. Okay, so this is what's happening in each round. However, it is important to note that the left side become the right side after performing the exclusive OR operation and after merging it with a key which has been passed through the function. On the other side, the right hand side, you see, we are not applying the function. Okay, we are actually applying the function on the right hand side along with the key, but we are not applying the function on the left hand side. So if you give some attention, it is like this. We have a function denoted by f, and it takes two things as an input. the first input is K1, and this K is derived from the K which is like the 56 bits. You see here, this is actually the Ki. In this case, this is K1. So this function take two input, K1 or Ki and R0, the right 32 bits of the input. And then it perform the function over it, and the output of this is exclusive OR with the left hand side. Okay, so it's like this. We have a function, it take two things as an input, the key and the right hand side 32 bits, and then apply the function, and the output is exclusive OR with the left hand side, and then it is provided as an input, or it become the next in the next phase it will become the right side for the next round. So here it is a bit difficult to understand, so that is why we are trying to understand it from this single diagram. So you can see we have 32 bits left hand side and we have 32 bits on the right hand side. It is denoted by L0 and R0. In the first round, what's happening? We take the key and we take the right 32 bits and we perform the function over it, and the output is exclusively ORed with the left hand side, and then the final output is provided to the right hand side. So you can see the right hand side now in the next round, R1 is equal to the left hand side 32 bits denoted by L0 and exclusive OR along with the function, and the two input for the functions are R0 and K1. However, the other side is simple. R0 will become in the next round it will become the left hand side without applying any function, without applying an exclusive OR operation on it. So it is like this has to go through 16 rounds, total number of rounds, and this step actually happen in each round. Each round of DES is actually facile cipher. This operation is actually from the cipher, as I just mentioned in the history, which is known as fascial cipher, and this thing actually, this is the logic of the fascial cipher, and you can see here the explanation of the single round from a different angle. The round, you can see it actually takes L I minus 1 and R I minus 1. It's like the 32 bits of the right hand side from the previous round and 32 bits of the left hand side from the previous round, or you can say initial permutation box, and then it will create Li and Ri, which go to the next round or the final permutation box. So this is actually the F function. What's happening here, you can see, is like we get the key, we get the R, we apply the function, the output is exclusive R with the left hand side, and then it is swept. So actually the fascial cipher has two things, mixture and sweeper. Sweeper, left become the right, right become the left. Okay, and mixer, actually we are applying permutation and things as boxes so that we can mix the bits in order to make it secure and in order to achieve the confusion and diffusion properties. So this is what's happening in one round of the DES algorithm. Next important component of the DES algorithm is the F function. Okay, we studied initial permutation and final permutation, and then we explore the concept of a round, what happened there. Now it's time to explore the F, this function. So the F function, actually this is also known as the DES function, it actually applies a 48-bit key. You see here, it actually applies the 48-bit key, okay, to the right most 32 bits, and it actually produces an output of 32 bits. This function is actually made from 4 components. The first component is the expansion or E table. The second component is the exclusive OR that actually aids the key. The third component, which is very important, is the substitution or choice boxes, which is also known as S boxes. And the final component is permutation P. This F function plays a crucial role in the security of the DES. In every round of DES, a 64-bit block is divided into 32 bits each, and they are named as left and right block. Since each round utilizes a key of 48 bits, it is necessary to enlarge a block to be equivalent to the key size. This is technical. Let me revise. What is the size of the input text? 32-bit. What is the size of the key? 48-bit. So they need to be compatible. Either we need to make it 32-bit or we need to make it 48-bit. So what we are doing here, we are converting this 32 bits into 48 bits. How is that possible? That is possible with the help of expansion or E table. So let us see what is E table and how it converts the 32 bits into 48 bits. Here we go. Expansion table. So what you see here, we have as an input, it will accept 32 bits and it will convert them into 48 bits. 32-bit is expanded into 48-bit. And how it is achieved? This actually make use of this table, which is known as E table or expansion table. And you see that the port number here are actually numbered from 1. In the input it is number from 1 to 32, and here it is number from 1 to 48. Okay, so how it works, how it is expanded? Very simple. Some of the input goes to more than one output. Here you can see some of the input, for example 4, it goes to more than one output, and that's it. That is how we achieve. That is how we convert 32-bit into 48-bit, by using this table. For example, the value of the input bit 5, it becomes the value of the output at bit number 6 and also at bit number 8. So it takes 2 locations in the output. So the expansion box actually increases the diffusion behavior of this. Why? Because certain input bits influence 2 different output locations. As given in the table, you can see that exactly 16 of the 32 bits appear twice in the output. How? 32 plus 16, you will get 48 bits. So in the output we have 48 bit. So it's mean that 16 bits appear twice, and this will make the diffusion behavior of the disk, or it will increase the security of the disk. However, it is important to note that an input bit will never appear twice in the same 6-bit output block. This is one block. Sorry, this. No bit will appear here twice. That is a rule for the S boxes. So for the E boxes, sorry. So this is how expansion works. In simple word, it will convert 32 bits input into 48-bit output. Why? So that we can make it compatible with the key size. 32-bit, 48-bit, and the key is also 48-bit. And then we have to apply the exclusive R. So the next function the next component of the F function is exclusive R operation. And this is simple. After the expansion permutation, this actually uses the exclusive R operation on the expanded right side. Remember, the exclusive R operation is actually performed here. You can see it is actually performed on the right hand side. We take the right hand side. Okay. And the round key is also taken as an input. So exclusive R will take two things as an input: right bits, 32 bits, which has been expanded to 48 bits, and the key, 48-bit key. And note that both the right section and the key are 48 bits now. Okay. And also note that the round key is used only in this operation. The key is only used in this operation. So that is the role of the exclusive R. The next function of the F function is S boxes. This is the heart of the DES algorithm, the S boxes. S boxes do the real mixing, which means the confusion. This algorithm uses eight S boxes, and each S box will contain some data, and it has a proper format. So you can see each S box takes 6 bits and give 4 bit. So it converts 6 bit into 4 bit. Or in other words, you can say it will convert 48 bits into 32 bits. Okay. Why we are converting 48 into 32? The story begins from here. Initially, we have 32 bits here. Okay. But the problem was that the key was 48 bit. So we expand the 32 bit to 48 bits. And then we exclusive R with the key, it gives 48 bits. And then you can see here, we are passing the 48 bits from the S boxes, and again we are getting 32 bits. Why? Because the input is of 32 bit. So finally we need 32 bits. So that is why the S boxes are there. You see the symbol is like we are getting less bit and we are converting it into more bits. We are getting more bits and we are converting it into less bits. So again 48 bits are converted into 32 bits by using the S boxes. So that is the primary role of the S boxes, although it is important for security purposes as well. So here let me revise. 48 bits are given as an input and 32 bits are actually taken as an output. How that work? S box, there are 8 X boxes. Each S box will take 6 bits and it will convert them into 4 bits. So the process is also depicted from another angle like this. Hey, we got 48-bit keys, we got 48-bit input text. Remember, initially we have 32 bits, but we expand it in this phase. We expand the 32 bit to 48 bits. So we have 48 bits. And now again, exclusive R operation is performed here in this step. And after that, here is the exclusive R. Here is the exclusive R. Here is the exclusive R. Okay, so after that exclusive R operation, we are providing the input to the S boxes. Okay, each S box contains 64 entries. 64 entries are here, 64 are here, 64 are here. And they are typically represented by tables. Each table, this is S1, S box 1, S box 2, 3, 4, 5, 6, 7, 8. And each table will contain 64 entries. Okay. And they are represented by tables. And each table will contain 16 columns and 4 rows, starting from 0 here. Starting from 0 up to 15, 16 columns. Starting from 0 up to 3, 4 rows. So 16 columns and 4 rows. Each table will contain it. Okay, we are using the integers starting from 0 to 15 in each of each entry in the table. Actually, they are represented in decimal notation form, and it is actually a 4-bit value. Each entry is a 4-bit value. All S boxes are different. Important to remember. Okay, now again a question. Why we use these S boxes? Why we choose these S boxes, or why the designer has chosen 8 S boxes? It was never completely revealed. Okay, this is a secret. Nobody knows about it. However, what we know is that each S box has 6 input bit and 4 output bit, and they are numbered in decimals and things like that. These are the things that we know, and many other things. But the secret, the logic behind using them are not known. Now another question is how the 6 bit are actually converted into 4 bits. So we are using the table there. We are given, for example, we have given a number like this 1 0 0 0 1 1. How many bits are here? 6 bits. Okay, so you know we have a most significant bit and least significant bit. So the most and least significant bits of this number, they actually correspond to the row, while the remaining in between 4 inner bits, they actually represent the corresponding column. So the most significant and least significant bits, they represent the row of the table, while the inner 4 bits, they represent the column of the table. How? We have an example here, a very simple example. Suppose you have this input, as I just mentioned. So what is going to be the output? And this is going to be, we are going to consult S box 1. So first thing is that consider the least significant and most significant bits. They are 1 1. So 1 1 is in binary, and 1 1 in binary is equal to 3 in decimal. Okay, and the remaining 4 bits 0 0 0 1 0 0 0 1 in binary, that is actually equal to 1 in decimal. So we have a row here and we have a column here, and which table we are going to search for? S1. So go to row number 3. First we have to look for the value in row number 3. So here we go, row number 3, and then which column? Column number 1. So this is row 3, column 1. What is the value here? The value here is 12, which is again in decimal. Okay, so we need to convert it into binary. So the binary output is going to be 1104 1100. So this is 4-bit. We take an input of 6-bit and we convert it into 4-bit. That is how S box will convert any 6 bits into 4 bits. Another example for you to try on. Okay, so this was the concept of S boxes. The next component of the F function is actually a permutation, but we will not go into the details of that, as we will see, as we have already seen the concept of permutation. Okay, next component is subkey generation. Let me go back. So we start our journey. We studied initial permutation, final or inverse permutation. We studied the F function. We studied the rounds. Now it's time to explore the concept of the key. For each round, we are actually generating a subkey. So subkey generation. And this subkey generation is based on the following operation. What are those operations? They are mentioned here. Permitted choice 1 and left shifting. PC1, left shifting, and PC2. Here we go again. Permitted choice 2, permitted choice 1, and left shift operation. Okay, these are actually tables. Where we were. Okay, PC1 and PC2 and left shift. These are actually the operation for which are actually performed on the subkey generation. Permitted choice 1 or PC1, it actually takes the 64-bit symmetric key from the user. The 64-bit is first reduced to 56 bits by ignoring every 8 bits. As I just mentioned, they are used for parity purposes, so we have to consider only the 56 bits. And permitted choice is something which is happening here but not shown in the figure. So we have PC1 table here, which actually take the 64-bit and convert it into 56-bit. And for date, we have a standard table available that is shown here. You can see the values here. The concept is same. This bit is going to be to take first location. Okay, so actually we use this PC1 table, and the first entry in the table is 57. This means that the 57th bit of the original key will become the first bit of the permitted key, just as we saw with the plain text. So the concept is the same. Similarly, 49 bit of the original key will become the second bit of the permitted key, and so on. This PC1 table, if you give some attention to the numbers, to the digits, you will not find the digits 8, 16, 24, multiple of 8 are not there. Why? Because they are used for parity. Okay, so we have 1 here, we have 2 here, we have 3 here, we have 4 here, we have 5 here, we have 6 here, we have 7 here, but there is no 8. And similarly with 16 and 24 and so on. Next operation is the left shift, and this is simple. The permitted key, the output key from the PC1 is actually shifted to the left, as you can see here. Okay, we are applying the left shift operation. So actually we are shifting the bits to the left. But how the bits are moved? There is a standard rule. Each bit moves one place to the left, except for the first bit, which is cycled to the end of the block. And this is very useful for decryption keys schedule, where the subkeys have been generated in reverse order. So how the shift process works? There is a standard rule. In round number 1, we have to shift only a single bit. In round number 2, we also have to shift a single bit, and then for round number 3, 4, 5, 6, 7 up to 8, we have to use a double shift, and then 1, and then double shift, and then 1, and things like it. So it is predefined in the disk. And then we have the final step, which is the permitted choice 2 or PC2 table. After the left operation, both the separated blocks are combined together, which will again form a 56-bit key. They are rearranged and then shrunk to produce 48-bit key. And this permitted choice 2 is performed by using this table. So PC2 actually permutes the 56 bits, which is coming from, as you can see here, which is coming from CI and DI. And why we have converted the 56-bit into 48-bit? Remember the concept? Because 8 bits were removed, because they are used for parity checking. So there is the concept of the key generation. Now let us move and quickly review some of the drawbacks of the DES algorithm. There are two criticisms on the DES. the first criticism that we make on the disk is that there is something which is related with the key size that is used in the disk. Key size matter. The description of the disk which is published makes sound that this algorithm is going to use 64-bit key. However, it doesn't use 64-bit. Instead, it uses 56-bit. Why? Because the remaining 8-bit were used for error checking, parity check. So the first critic questioned is the small size of the key, only 56-bit. Why not to use 128-bit to 56 bits? The longer the key size is, the more secure the algorithm is. So it make the cipher vulnerable. It make this algorithm vulnerable to brute force attack. One of the security person, Diffie Hellman and other, they have objected this key size. They claim that this is inadequate to resist a brute force attack. Even if we are using super purpose computer, then it's become very easier to perform a brute force attack on the disk. So that was the first objection, key size. Second objection is the secrecy of S boxes. As I just mentioned that there is some hidden design elements in the disk algorithm and their internal structure was never revealed, and it becomes suspicious that some part of the structure, the S boxes, may have some hidden, remember the concept of the trapdoor, backdoor. So people start thinking that there must be some hidden trapdoor in the S boxes that would allow the NSA to decrypt the messages without the key. So cryptologists also express concern over the secret manner in which the S boxes were designed. And they suggested two things: that the NSA should make the design of the S boxes clear to us, or they should create a new S boxes in some manner. Later on, the IBM designer also mentioned that the internal structure of the S boxes, they was designed to prevent different types of cryptanalysis attack, but that doesn't satisfy the security related persons. So instead of the widespread use of the disk, this problem prevented the disk implementation from a universal acceptance. And to address this limitation, triple disk was introduced. So if you are interested to study this topic, you can study it at your own. It is also known as 3-disk or triple disk, and it was developed to address the flaws in disk without designing a new whole crypto system. And it was the first standard which was used for financial applications in 1985. And triple disk was incorporated as part of the data encryption standard in 1999. The procedure for encryption is exactly the same as used in the disk, but 3 times, repeated 3 times. That is why the 3 is here. Like the disk algorithm, data is encrypted and decrypted with 64-bit plain text chunks or blocks. However, the key size of the disk was increased. Not increase in the sense, but it's like a triple disk involve using 3 64-bit keys, and they are known as K1, K2 and K3 in each round. Instead of using a single key, it will use 3 keys. So it means we are like tripling the security of the algorithm. Okay, so if you're interested, you can dig this topic on your own. Thank you so much for attending the lecture. Take care and goodbye.